So in the first look video that I did on the IKEA LADDA 1900s and the IKEA LADDA 2450 AA cells and the 750 milliamp hour AAA cells, the ones we'll be looking at today and that were tested were the 1900 and the 2450s. There'll be a separate video for both the 750 milliamp hour and the 900 milliamp hour. These I haven't tested yet. So those of us that had the previous generation, or if there's still old stock out there, you'll be able to see how those performed, which I'd expect them to do pretty well, considering how well the previous generation or previous color LADDA 2450s did. Today, just the AA cells, and primarily the focus is going to be on the LADDA 1900 cells, the new ones, because I was very curious to see how they performed in comparison to the, you guessed it, the Eneloop 2000 milliamp hour cells, the standard Eneloops. These are from 2018. So I bought these. These particular ones are the 4th generation BK3M CCA, minimum capacity 1900 milliamp hour, nominal capacity 2000 milliamp hour. And we're going to look at the results of these. And then I also tested 4 of these as well. I have about 20 of them. I'm going to test them all at some point. This stuff takes time, so I was only, for this video, after a couple of weeks, it's the result of testing 12 cells for both the capacity testing, the internal impedance measurements across a broad range of current loads. That took quite a bit of time. I'm excited and very interested to do the remaining testing. Let's talk about the LADDA 1900s. I ran these for 10 charge cycles. Actually, I think it was 12. I wanted to get at least double the 3 to 5 recommended charge cycles that most manufacturers recommend prior to running any sort of tests on them, so that we get an accurate capacity, because the cells need to kind of, they've been formed, they've been tested in the factory, they've been charged up, and then they need a couple of cycles to get themselves into a state that actually gives you a meaningful number. For the 1900s, I'm quite impressed. I ran them through the 4 test profiles like I've been doing with the Lacrosse Technologies BC1000, which I don't think I can actually, nope, that will not move any farther than I can just take it out here and unplug it. The cable's so short, but this is it right here. It's been used for all the testing to date, and ran it through the 4 charge discharge profiles that it has. The 100 milliamp discharge current average was about 1.92 amp hour, with all the cells coming up over the 1900 milliamp hour capacity. Off to a good start. The 250 and 350 milliamp hour discharge currents were at 2.08 amp hour average and 2.12 amp hour average, which is good. It's above what the label rating is. And then at the 500 milliamp hour, it came down a little bit to 2.10. Awesome. How does that compare to the Eneloops? Well, let's take a look at those. So here's the Panasonic Eneloops, the 2000 milliamp hour, and these are 3 years old. So they've been used they're probably in around 100 to 150 charge cycles over 3 years. So definitely got a good amount of charge cycles in them, but they're way under their 2100 charge cycle maximum before they hit 80% total capacity. Interestingly, they eked out 1/100 of an amp hour more average on the 100 milliamp discharge current, but it's important to note that there's more variability there than there was with the IKEA LADDA. So there was the first that was at 1.88 amp hour, which fell below the 1.9 minimum. And then you had one cell that was kind of like 1.95. So there's some variability there. It's there as a function of aging cells. Again, get subscribed so that you can see, because I'm going to run 20 of these cells through all this testing to see if that bears out over a much larger sample size. But for right now, with 4 of them, the average is 1.93, which is, I would say, it's within the margin of error of the tolerance. So they're pretty much right on with each other at that 100 milliamp discharge current. As we go up to 250 and 350 milliamp discharge currents, the capacity climbs to 2 amp hour and then 2.1 amp hour, so a little lower than what the IKEA LADDAs were able to achieve. And then at 500 milliamp, it fell back kind of in the same way that the IKEA LADDAs did to 2.06 amp hour and Capacities are pretty much on par with one another. Let's just take a look at the graphs here. We got some pretty graphs, so why not make use of them? Here's the graph. The first is just the graph showing the capacity of the IKEA LADDA Gray 1900s. And you can see that they're pretty uniform between cells. So you might get one that's a bit higher or lower than the other, but as you go up in discharge current, you can see visually that they're pretty much uniform and consistent with one another, which is what you want to see. You don't want to see things like what we saw with the power owls, for example. Let's just put that graph up there for a moment. You know, where you see capacities all over the place, right? You see a huge amount of variance even as you go up to the higher current discharges. Okay, last graph here for the IKEA 1900s, and it is the IKEA 1900s come right up against the 4th generation Eneloops. I also included the plus or minus 5% tolerances, so you can kind of see that these batteries, I would expect that sort of a tolerance in their capacities. They don't mark them anywhere, but you know, it's important to include for perspective the plus or minus 5% there. So the net minus 5% is about 1.81 amp hour, and the plus 5% is 2 amp hour. And so, and in fact, it's consistent with what Panasonic showed, that they would say 2000 milliamp hour typical or nominal, 1900 milliamp hour minimum, which is a 5% difference. That's what I put up here, and you can see that they all fall within the 0% range. And then as you go up in discharge current, they go well above 0%, and some go above the 5%, which is pretty impressive. And actually hit 10% above their stated capacity at 2.1 amp hour. So pretty impressive there. All right, we're going to now shift over to the IKEA LADDA Grays, talk about capacity there, and then we'll move on to the internal impedance measurements, which is new and is pretty interesting. Here we go. There is a comparison with the IKEA LADDA previous generation or previous color. I don't really think it's a generation thing. I think it's just a different color, and they wrapped them in different colors because they introduced another version. They basically have the same thing, and here's the results to show that. The 100 milliamp discharge current yielded 2.43 amp hour, which, yes, it's a little bit less than what's stated on the package, but the Eneloop Pros and the previous generation LADDAs also encountered that, as you'll see in a second when I show the IKEA LADDA previous color results. At 250 milliamp and 350 milliamp discharge, everything rose up quite a bit to 2.63 and 2.68 amp hour discharge. And then finally at 500 milliamp, it fell back down to 2.58 amp hour, which is the only difference that I noticed between the dark gray cells and the white cells. If you look at the IKEA LADDA White, that they did a little bit better in that highest discharge current. So starting off at 2.45 amp hour, running up to 2.62, 2.67, which actually the newer cells did better. This data that I'm showing you on the IKEA LADDA Whites is actually the data that I used when I did the performance testing on those cells, and it was roughly about the same amount of time and charge cycles after I received them. So it's not like I'm testing them now after they've had 50 or 60 charge cycles on them or anything like that. The only difference is, and I think it might account for some of the variation in capacity, is that these were tested in winter, and the ambient temperature from the log data that I have was about 68 degrees Fahrenheit. And when I tested these, it was pretty hot outside, but the air conditioning was running inside here, and the average temperature was about 78 degrees Fahrenheit. So about a 10-degree temperature difference. So it could account for some of the difference in the capacity, but you only notice that actually at the highest discharge current. For the two middle discharge currents, 250 milliamp and 350 milliamp, they're basically the same. They're off by 100th of an amp hour. Yeah, the IKEA LADDA Whites at 500 milliamp discharge current ended with 2.71. But it had some cells that, you know, they only got to 2.68. Actually, that's pretty consistent there on the previous IKEA LADDA. So I'm going to get some more cycles into these, and then I might run them again in 3 or 4 months just to see how they're doing after they have more charge-discharge cycles on them. Let's look at the graph just to get some perspective here on the 2450s. So if you look at the 0% on this chart, you can see that pretty much the cells, they always came in above the 2.45 amp hour rating, with the exception of the 100 milliamp discharge. They're designed for higher power usages. it's understandable that on the lowest end of the range that I can test it on this with this charger, that they would fall just at that minimum capacity. So above that, up to 250 milliamp, 350 milliamp, and 500 milliamp discharge, they all fall well above that. Let's compare it to the IKEA LADDA White. The IKEA LADDA White 2450s are on the left, and the IKEA LADDA Grays are on the right. Again, I've included the bars of the plus or minus 5%. They all fall way above the minus 5% of 2.33 amp hour. And all the charge profiles, with the exception of the 100 milliamp discharge, they all came in well above the 0% tolerance. And then pretty much all of them were at the above 5% for all the other discharge profiles. It's interesting that last test, the 500 milliamp, the new LADDAs, it just was just above that 5% mark, whereas the white ones were higher than that. They kept climbing. I think it might be likely due somewhat to the temperature. These being tested in a cooler environment, 10 degrees cooler Fahrenheit, and these in kind of a bit of a warmer environment, and it may have just caused the cell to heat up and discharge a little bit faster. The internal impedance in these through most of its range can be considered linear, but it becomes nonlinear as you start to get into really high discharge currents, which I think is up to 4 amps on the 1900s and the Eneloops, and I think up to 8 amps on the LADDA 2450s if they're similar to or compatible or designed with similar technology that's contained within the Eneloop Pros. And that's a perfect segue into the last chunk of testing, which is the most interesting chunk of testing, I think, which is internal impedance measurements. Now, this is a new set of testing for me. I've been involved in a lot of battery management designs and designed some stuff myself. I didn't want just to do it with a battery tester or analyzer that could just run the test for me, because most of those, not all, but most of them tested at a particular fixed load impedance and then give you back an internal impedance value. And what I wanted to do was to set up to get a range across a variety of load current. I was able to set that up. I ran into some limitations. I'll discuss them briefly here, but there's going to be a separate video that's dedicated entirely to that setup and how everything's calculated. In this video, you're just going to get the charts and the graphs to show what the results were. Starting with the IKEA LADDA Gray. So I highlighted the important bits in green, and I ran it through 5 different target currents, which was 60 milliamp, 240, 600, 800, and 1200. And then this was cross-checked to make sure that there's a lot of things going on. So if you're interested in like how this actually was all done, and I'm not just making up numbers, get subscribed so you can be notified when that video comes up, because it goes into great detail as to how this all is set up and how you could set it up yourself too if you wanted to do this testing. Let's get into the details here. Each cell was tested 3 times in total. You only see it here once, but it was tested 3 times in total. So here we've got the 4 cells that have been tested. The averages are around the corner. I'm really going to talk only about the averages here. You can see that you start off with the 60 milliamp target current. The impedance is kind of high at 105.82 milliohm, but as you go up in target current, that impedance level drops to 84.5, 91.35, and then even lower as you go into higher current levels, 800 and 1200 milliamp, to 75.5 approximately and 72.9. I just took that, averaged it out, and got an average internal impedance for all the 4 cells across all the ranges, and that came out to 86.02. You can see in the graph that shows on the horizontal the battery internal impedance, and then on the vertical the various load current groups. There is some variability that goes on, but as you get into the higher discharge currents, it kind of stabilizes down, and that's due in part to the battery manufacturing variability and also a bit of variability with the equipment and the setup. This is not an absolute number to go off of or look at and say, okay, it's absolutely 86.02 milliohms impedance or anything like that, but it's a reference point to help give us a guidance of how these perform compared to Eneloops, which is the big question that everybody's asking. So this helps get us toward a yes or toward a no. The final thing was just to give a graph here of the battery internal impedance. This is just the graph of the load current on the horizontal now and the battery internal impedance on the vertical. And what it's showing is that what I'm operating in is kind of that linear region. There's the 60 milliamp on the low side and 1200 milliamp on the high side. And I know that these cells can be used with way lower load currents down to computer mice and keyboards that are drawing way less than 60 milliamps in little bursts. So be able to test that and to test way higher current discharges like up to 4 amps or 8 amps, well, I need different equipment and different components, which again, we'll get into that separate video. But I wanted to show that it's pretty linear. You can see that the impedance is dropping and the trend line has a pretty good R value, but it's about 0.8, so we're pretty close to linear. Now, let's look at the Eneloops for comparison. Same setup, same testing, everything is basically the same. And interestingly, with the 60 milliamp target current, the internal impedance is much lower at that level. It's 74.8 milliohms average. And then it climbs up a little bit to 80.3, and then it comes back down again to 74.3, and then up again, and then up at the end a little bit more. It's much lower at the beginning, and then kind of progresses across pretty linearly, and yields an average internal impedance of 79.1 milliohms. So between the two, we're talking about an 8.7% difference in average impedance. I would say plus or minus 5% of that is tolerance, just in the testing setup, the cells, environment, a lot of things. But there's between a 3 and 5% difference between these two when you remove all of the percent tolerances and uncertainty. So interesting. That's an interesting thing here to look at. So that's these batteries. We'll get these out of the way. Now let's look at the IKEA LADDA 2450s. That's the last one that I went through and tested because it was a lot of testing to do this across 12 cells. There's a lot of measurements to get this all put together because I wanted to test it and be able to repeatedly test it. Now, the one thing I didn't include in here is the temperature at which this was taken at. That has been recorded separately, but it's not in these tables. But I'll mention here that the temperature was 75 degrees Fahrenheit. IKEA LADDA Grays. Interestingly, I would have thought that they would have had a higher internal impedance at the lower target current, but it seems like they don't. I believe that's because we're operating in a linear region of all of these cells. And if I get the appropriate equipment and components to get down to a lower target current and then go up to a higher target current, we'll see that deviation away from a linear range. So we start off at 53.17, which is quite low, and then it climbs up a little bit to 58.02, keeps climbing even as we're going up in current. So 66.11, 69.21, and then it starts to come back down again at the 1200 milliamp discharge current. So you average all that out, get what I said before, 61.31, which is less, markedly less than both the Eneloops and the LADDAs. And we'll just go with the Eneloops and as the comparison here. So the LADDAs on paper show that they have a 22.5% lower internal impedance than even the Eneloops do, which is, yeah, it would be like, oh, that's just get these. But that's because we're operating in that linear range. And which I might be wrong, I don't know, but I'm expecting to see that if we go to a much lower discharge current, say 30 milliamps or 20 or 10 down to maybe 1 milliamp, and then up to like 2, 4, and 8 amps discharge, which we can't go to 8 amps discharge on the Eneloops because they're only rated to 4 amps, but we'll take them up to 4 amps. So if you want to see that, which I think is going to be pretty cool, that you'll see that we're going to see this deviation, and the Eneloops, as you go down to much lower discharge currents, are going to have a way lower internal impedance than these will, because these are designed for high current applications, and these are designed for lower discharge applications and will last much longer. So the data is what the data is. It gives us a picture of something. It shows us, oh, these are all very low impedance cells, low internal impedance cells. I mean, anything under 100 milliohms is pretty low impedance for a nickel metal hydride cell. And even Eneloop's own data sheets show that most of their cells are between 25 milliohm and 40 milliohm. But they have a different way of testing it, which I'm investigating and we'll talk about in a separate video. So let's look at the chart here. We can see a little bit more variability in the load current over the battery internal impedance. That's a little bit interesting. I think I'd like to get some more cells, maybe another 4 of these, another 4 of these to test out to get more data points, honestly. If we look at the battery internal impedance over the load current, and then we try to see how close we are to a linear region of internal impedance, you can see that it's not very linear. There's a lot of variability there. So then in the 1900s, we were really close. We had R value very close to 0.8, I think it was, 0.79. We saw a declining internal impedance as we kept increasing the load current. But on the LADDA Grays, it's showing about 0.37, and it's actually climbing a little bit and then coming back down. So this is, you know, as much testing as I can get done with what I had on hand and the amount of time that I had. But there's two takeaways from this internal impedance testing. One, I want to do more testing. But secondly, all the cells came out with pretty low internal impedance. I say that the dark gray LADDA 2450s are basically the same as the LADDA 2450s. They just changed the color of them so that they could introduce these 1900s, which are and so that there was a difference between the two, and there's no real functional difference between these two. And the internal impedance measurements really show that. They show that they're quite low internal impedance across all of these cells, which is very impressive. I'm going to buy more of these batteries. I think they're good batteries. The price is right. They're way less expensive than the equivalent of Panasonic cells. These cells, they perform very well. And just in day-to-day testing without all the data, putting them in high-demand applications like the best example I have is that air quality monitor, because it draws a lot of current when it's running. And I also have a couple of lights that draw a lot of current when they're running, and they perform as good as the Eneloop Pros. The Pros are probably slightly better, but testing will show that in the coming months when I do wider range testing with equipment that I can go in through a much broader range with. If you're out there looking for rechargeable batteries, they're a great buy for the price, and they will work very well in a wide variety of applications. I hope you enjoyed this video. If you have any questions or comments, leave them down below. If you like the video, please give it a thumbs up and please subscribe. And I will see you in the next one. Take care.